When you watched the video related to valence bond theory or read that section of the textbook, you might have noticed that there's a pretty serious problem with valence bond theory. And namely, that is, there's no way to get the bond angles that are predicted by VSEPR by using valence bond theory. To discuss this, we're going to look at a carbon with 3 bonding domains, 2 single bonds and a double bond. We know from VSEPR theory that this structure has 3 bonding domains, and it should therefore be a trigonoplanar structure with bond angles that are close to 120 degrees. So the question becomes, how do you get angles of 120 degrees when we know that the orbitals that are involved in bonding are going to be s orbitals and p orbitals, which will look something like this? The s orbitals are all spherically symmetrical, and the p orbitals are all dumbbell shapes that are oriented perpendicular to one another. And you have to ask yourself, how can you combine these angles to get 120 degrees? And the short answer is you can't. So we have to learn a new model of bonding that will account for the angles that we see in real molecules. And that new model of bonding is known as hybrid orbitals. The hybrid orbital theory of bonding isn't perfect. It has a number of flaws, and we'll discuss some of them later. But it works pretty well for organic molecules, so that is carbon-based molecules. And because it works so well for organic chemistry, you'll see the model very frequently, so it's worth learning about. The hybrid orbital model relies on the idea that the atomic orbitals within a central atom can hybridize with one another to make new orbitals that have characteristics that come from the individual atomic orbitals. There are 3 different types of hybrid orbitals that we'll be talking about, and those are the sp orbital, the sp2 orbital, and the sp3 orbital. The sp hybrid orbitals are the result of an s atomic orbital hybridizing with a p atomic orbital. And these sp hybrid orbitals contain 50% s character and 50% p character. And this is reflected in the shape of the hybrid orbital. It has some dumbbell characteristics, like you would expect from a p orbital, but one side of the dumbbell is much larger and more spherical than the other, and that is the expression of the s character of that hybrid orbital. The sp2 hybrid orbital results from the hybridization of a single s atomic orbital and 2 individual p atomic orbitals. So the hybrid orbitals have 33% s character, 1/3, and they have 66% p character, 2/3. And this is again reflected in the shape. So it has a dumbbell shape coming from the p character, but there is some s character still present, and that causes one lobe of the dumbbell to be a little bit larger and more spherical than the other. The same kind of hybridization process is involved in the sp3 hybrid orbitals. These are formed from the hybridization of a single s atomic orbital and 3 individual p atomic orbitals. And that means that they have 25% s character and 75% p character, and again, that's reflected in the shape of the hybrid orbital. And any of these hybrid orbitals can overlap with either hybridized or unhybridized orbitals in a way that's similar to that described in valence bond theory.